Namaskar my dear friends. Let's talk about PWM controllers. So as you know, PWM controller can be utilized in your switch mode power supply, that is SMPS design, or general purpose DC-DC converter, or offline isolated power converters, or we have lot of board mount power modules. Okay, so basically it can be used as switching regulator also in several cases. And why do we use this kind of PWM controller is it is because of very low cost and very simple to design. There are a lot of like SMPS converters are there these days, which are very advanced one. However, with low cost design and very like consumer applications and industrial applications, these PWM controllers are very much preferred. So I'm going to take up one of the controller which is UCC series, which is UCC28C44. There are a lot of other parts as well that we'll discuss up. Okay, and let's say UCC28C55 is also there, which little bit upgradation. So what we'll do is we'll try to understand with this particular IC what are the different parameters that we need to take care of and how to design the very simple circuit using PWM controllers. So it is low power current mode PWM controller. We'll also discuss voltage mode PWM controller. Okay, voltage mode PWM controllers. So let's get into the little bit of understanding what are the different devices that is available with this particular series. So as you can see, we have UCCx8C4x. It means we have UCC28C40, then 41, 42, 43, 44. Then we have 45, and then it comes up 30, right? So 28, 38. So 38, 40, 38, 41, 42, 43, 44, 45. So basically it starts from 40 onwards up to 45, and 28 series also 42, 44, 45. Okay. What are the differences that is there with all these devices is basically the turn on voltage and turn off voltage. Basically the over voltage, at what place it will turn on, like under voltage lockout, under voltage lockout. Okay, that is one of the difference. You can see, yeah, it is written under voltage lockout. So our main purpose would be to concentrate on this particular device, which will be UCC28C44. Okay. And generally you can see there are two types of duty cycle. One is 100%, which is actually equal to your switching frequency that you have set, and one will be half of that, that will be switching frequency divided by 2. Okay, so that will be the duty cycle that we can always set. Let's see a very simple circuit that we can look into, and we can start with. Basically what will happen is you have the UCC device, so you will be required to give a voltage here. Well, let's say here we are going to give 15 volt, or let's say 12 volt. Okay, and then this is going to go to power up this particular device through VDD pin. Okay, so this is my bulk capacitor, this is can be working as a smoothing capacitor, and this is the inductor that you will be simply taking up. So this inductor is going to get switched on because of this MOSFET. Okay, Q2. So this MOSFET will be switching on based on this output pin, and the RT and CT pin has set a frequency, switching frequency, that will be utilizing this output gate switching. Okay, so this is kind of a gate driver as well, you can see. So this is a gate driver, So PWM controller is nothing but a gate driver which is going to enable you to have a capacity or capability of having little bit higher current and higher voltage levels to drive the gate of the MOSFET. Okay. Now there is a beauty of this particular IC is like we have to have current sensing. So the what is the current flowing through this drain to source. So this current sensing resistor R12 can be utilized to do that current sensing through that. Now what do we do for the output regulation is basically we have feedback resistor which is R9 and R13. So this R9 and R13 voltage divider is going to go to feedback pin, which is going to give you at at the error amplifier to regulate the output voltage, which will be around 2.5 volt. Now there is a compensation pin as well. So this compensation pin actually is going to give you the output to error amplifier inward inside of this particular UCC28C44 PWM controller. So this is RC combination is going to compensate that. At the same time, this particular compensation pin can be used to switch on this particular uh, PWM controller also. So if you want to switch it off, you can put it low and you can put it high whenever you want. Switch off, switch on. Okay. So that's how we'll see those applications as well. But this is the particular very simple understanding I am telling you. Now let's get rid of all these things that we just now learned. Now what we can do is, generally what happens in our flyback converters or all those kind of converters is, basically this particular block will be shifted with some AC source. Okay, so we'll see that. Let me get into simple SMPS design block. Okay, so what happens in simple SMPS design block? We have our one AC input, and this AC input is going to go ahead with safety safety fuses or CMCs or X capacitor, Y capacitor, all those things. We'll have some filters, okay, like common mode chokes or line filters and all those things. Then what happens? We send it to my bridge rectifier, which is going to rectify the voltage, right? So this is a simple block that we always follow. And what happens after that? We have the transformer block. So this transformer block will be there, which will be kind of like buck converter, or like buck type or flyback type or boost boost type or forward type, whatever kind of converter that you want to have. And generally it is going to go ahead, let us say if I am talking about flyback, then what happens? This flyback rectifier will be used, and after that we will be having one filters like capacitors and like inductor or ferrite bead or something like that, and capacitor, bulk capacitor will be there, and then we are going to take out the output. So this is what the simple thing is. What are the other things that we do? Basically we will have one switching device, which will be like basically generally a MOSFET will be used. So this MOSFET will take care of switching of this particular transformer, and this switching of MOSFET is taken care by the device which is called PWM controller or gate driver. Okay, so this PWM controller will take care of the switching of this particular MOSFET, and at the same time the power supply on all these things will be supplied from let's say here with some voltage divider or something like that, like VDD or something that we will see always. But this is the main block that we are going to look into. We'll just delete this. Okay, and how it is actually going to convert is, we will be having some feedback here. So this will be working as feedback. Either it can work as a voltage divider or with non-isolated ones. If you want to have isolated one, then you will be using some optocoupler also in between, and then we send it to the feedback pin of PWM controller. And since it is sent to feedback pin controller, it is automatically going to have a closed loop a control system, and this closed loop control system is going to give you the specified output that you have designed for. So this is a very simple SMPS design block that we generally use. And what are the different things that we try to make it more stable, as well as much more fine tuning design, that we always look into later on. Okay, so what we'll do is, basically our aim is to understand this particular device, which is UCC28C44, and this device, what are the different parameters, features, and how we can design our SMPS using this particular device, that we will see. So before that, what we'll do is, we'll try to understand what are the features of this particular device. So let's make it little bigger. As you can see, we have enhanced replacement for, there are always already one device which was UCC2844 directly. Now they are going to convert it to UCC28C44. So this is like actually the advanced one. Okay, and this has been very popular device for past 2-3 decades. Okay, and the same thing, this is going to carry forward the legacy of this particular UCC series. You have the operating frequency up to 1 megahertz maximum, and you can see we have very low operating currents and all, and then we have fast cycle by cycle over current limiting, okay, which is going to be 35 nanosecond. We have peak driving current of ±1 ampere, so it can give you a driving current for the gate MOSFET up to 1 ampere. We have 25 nanosecond rise time, 20 nanosecond fall time. And the best part that we see here is plus minus 1% 2.5 volt error reference. That is nothing but your feedback pin which you will be comparing your output so that you can regulate a proper output voltage. We have trimmed oscillator discharge current, we have under voltage lockout protection, so the device will start only when it reaches to a particular voltage level, otherwise it won't start. And we have VSSOP package also, as well as we have SOIC package. So we are going to discuss with SOIC package, but VSSOP package is bit smaller compared to that one. Okay, and we have this all application is already there, so we can remove it. So we have like board mount power supplies, like on a small PCB, suppose we need one PWM a PWM controller, so we can use this particular IC and convert your output to your particular level that you want it. Good. If we talk about the package information or pin description, there are two things. One is SOIC package, one is VSSOP package. Okay, and you can see we have like UCC28C 4 series and 28C38 series also. Sorry, UCC38 series also. So VSSOP package is smaller compared to the SOIC package. The pin configuration of SOIC and VSSOP both are same, so design will be actually same. However, these are the pins that we have. So we have compensation pin, feedback pin, current sense pin, we have RTCT pin which is going to use for frequency setting, and we have V reference pin which will be actually going to give you a output voltage of around 5 volt, and that is used for some external purpose also if you want to utilize let's say pull up resistor or something like that, and for mainly internal circuitry analysis or circuitry power supplies. We have VDD pin which is my power supply pin, and we have output pin which is going to drive the gate of the MOSFET, and this is my ground pin. So one of the thing that it can be used as enable pin is compensation pin. So compensation pin can be used as a enable disable pin also at the same time, compensation pin. If we look into the details of each and every power pins, you can see compensation pin. So this pin provides output of an error amplifier for compensation. In addition to that, the compensation pin is frequently used as a control port. Control port means it can switch off or switch on the device itself by giving you a zero duty cycle, or if you want you can externally force it to ground. So basically if you force it to ground, you will be having zero duty cycle, and this is how it will be switched off. So it will help you to switch off the or shut down the device. We have current sense pin which will be connecting the gate resistor, let's say this is my current sense resistor that will be used, this is my RCS, so this can be used to sense the current through the CS pin. So we similarly we have other pins also. V reference pin, as I was talking to you, so if you see V reference pin is 5 volt reference, and this can be used to provide charging current to the oscillator timing capacitor through the timing resistors. Okay. Also you have to have a minimum of 0.1 microfarad ceramic capacitor required additional to this particular V reference pin if you want to load with some external loads on V reference. Very important thing that we always have to look into is we have to see the absolute maximum rating of this particular IC. So if you see absolute maximum rating, we have input voltage maximum 20 volt. You should not stress your pin more than 20 volt. We have input current as 30 milliamperes. We have output drive capacity maximum plus minus 1 ampere only. So you have to understand that the driving capacity of the MOSFET, that will be of the gate of the MOSFET, will be not more than 1 ampere. Then we see we have the output energy capacity which is up to 5 microjoules, and we have analog input voltages and all those things, so that is all limited to 6.3 volt for compensation pin, current sense pin, feedback pin and RTCT pins. We have output drive voltage, so which is going to give you up to maximum 20 volts. So whatever the input voltage that you are applying, same voltage you can get it at the output to drive the gate of the MOSFET. We have reference voltage pin which is going to be maximum 7 volt. Okay, and similar to that other pins are also there. Alright, we have error amplifier output sink current. So sink current it can take up to 10 milliamperes, and you can see we have the total power dissipation capability up to if you see 72 degree centigrade per watt and 98 degree centigrade per watt for D package and DGK package. So one is like SOIC package and one is VSSOP package. Okay, so it can this particular device can work up to 150 degree centigrade, so not a problem. Let's talk about recommended settings. So the recommended operating condition is nothing but we have to apply maximum 18 volt. So basically whatever we have designed for our several application, like we have used this particular UCC28C 44 and UCC28C55, which we will be discussing maybe next session in several projects of our like consumer goods or consumer applications and industrial applications with these devices. Why? Because of this is very low cost design and as well as very easy to design. Similar to that, you can have output voltage is up to 18 volts. So generally what we give at the input voltage VDD is we have always applied around 15 volt or sometime 12 volt, something like that. These two voltage ranges are generally utilized for most of the applications. The reference voltage, you can see we have 5.5 volt maximum. Average output drive current will be I out, which is going to be 200 milliamperes, and we have I out reference. You can take only 20 milliamperes, so you have to understand that V reference is not utilizing for more than 20 milliamperes of like current. That's all, and it can work up to 125 degree centigrade maximum, which is going to be 28 series, and 38 series will be working up to 0 to 85 degree centigrade. So 38 series will be lower cost compared to 28 series. If you talk about the thermal data, so you can see we have junction to ambient thermal resistance. So for SOIC pin it is 128 degree centigrade per watt, and for VSSOP pin it is bit higher, which is 170 degree centigrade per watt. Okay, so SOIC package is preferred, and this will be little costlier compared to VSSOP package. However, this is the like a data that is available with us for the junction to ambient thermal resistance. Okay. So SOIC package performance will be quite better compared to VSSOP, but to reduce the cost you can always go ahead with VSSOP, where there is no like temperature problem, like there is no temperature increment in the device because of like switching or something like that. If we talk about the electrical characteristics, so in electrical characteristic what we can do is just let it make little big. Okay. So you can see we have VDD as 15 volt. The conditions are what is given is, and then RT is 10 kilo ohm, CT is 3.3 kilo ohm, 3.3 nanofarad. We have CVDD is 0.1 microfarad, and this is the conditions that they have utilized. And then with that, what is going to happen with all the parameters? So V reference is going to go ahead with 5 volt. Okay. Line regulation, load regulation, all those things are fine. What we are going to get interested into is output short circuit current. It can go ahead up to 45 milliamperes. Okay, and you can see initial frequency is going to be 53 kilohertz. So what is the thing that is set is for CCT of 3.3 nanofarad and 10 kilo ohm of RT, you are going to set your oscillator frequency to 53 kilohertz. Okay, so if you are working with a 53 kilohertz system, you can directly use this RT and CT resistors and capacitors. Okay, moving to the next one, we have other parameters like VFB, feedback voltage. So feedback voltage, as I already told you, it is 2.5 volts. You have to understand during the design of your voltage divider at the output pin. So this is going to go to V feedback, and this is my R1, this is my R2. So value of R1 and R2 will be designed in such a manner that my FB pin will be just around 2.5 volt to regulate the output voltage of of the system which we want it. Okay, as you can see, we have open loop voltage gain, which is going to be 90 dB typical values, and we have PSSR. Good PSSR is there, minimum 60 dB you are getting PSSR, so generally it is very good parameter. For VDD range of, you can see 12 volt to 18 volt. we have high level compensation voltage, low level compensation voltage. So you can see maximum you are going to go ahead with 1.1 volt for low level, and minimum you are going to go ahead with V reference minus 0.2, that is 4.98 volt, right? 4.8 volt, right? If you talk about more other parameters, so we have current sensing. So you can see ACS gain is around 3. So typical values of current gain of the resistors, I mean current gain to sense the current or to monitor the current through the drain to source of your MOSFET is going to be 3. Then we have maximum input signal, that is going to be 1 volt. Okay, it means my VFB must be less than 2.4 volt. In that case, whatever the current that is entering into the CS pin, which is going to be 1 volt. It means what I want to tell you here is, what does it mean is, basically this is the current sense resistor, let us say RCS, and this is the gate of the MOSFET that is being driven. So this CS pin, so the voltage drop across this typically is 1 volt. So accordingly you have to design your RCS like a current sense resistor in that fashion for the current that you want to flow through the, not here, sorry current sense resistor is connected at the source of this. Okay, so basically you are going to design drain to source of the MOSFET to see what is the current that is flowing through the current sense. Hope you have now a very good understanding about how to connect your current sense resistor very easily and then send it to the current sense pin to monitor the current through the drain to source of the MOSFET. This is my drain, this is my source, this is my gate, which is going to get driven by my output pin. Okay, all right, so these were all the things that we have seen. The maximum that you can achieve with this particular device is around 96%, and for other pins, like whatever the device that we are using is C44, so that will be 48%. It means less than 50%. Okay, good. So this was all about the particular parameters, electrical characteristics. Now let us see some of the parameters that we have to set, like what is the graph that we can be using. So if you talk about typical characteristics, one is the typical characteristics for output oscillator versus timing resistance and capacitance. Okay, so let us say if you want to use 1 nanofarad of capacitor, okay, CCT will be 1 nanofarad of capacitor, then this curve you can utilize. Okay, and in this curve if you see, then what is the resistance that will be required for what is the value of oscillator frequency that you want to use, you can utilize this. So let us say if you want to use 100 kilohertz switching oscillator frequency, then it will be this point. Okay, and this point if you directly plan it here, so it is going to be around 15 kilo ohm. Okay, so you are going to see FSW will be 100 kilohertz, my RRT will be 15.1 kilo ohm or something, and CCT will be this and this is how your output switching frequency will be 100 by 2, that is 50 kilohertz. Okay, so this is my oscillator frequency FOSC, and this will be my FSW. Understood? So this is going to be FOSC, that oscillator pin frequency. So if you want to have a calculation, like I can show it to you. Let us say your RT resistor must be between 1 kilo ohm to 100 kilo ohm, that you can see here from the graph, 1 kilo ohm to 100 kilo ohm. Okay, your oscillator frequency must be set to less than 1 megahertz, that is 1000 kilohertz. Your CT, that is the capacitor, will be used from 220 picofarad to 4.7 nanofarad maximum. As you can see, we have 220 picofarad to 4.7 nanofarad. Okay, and then if you want to design for, let us say, oscillator frequency of 110 kilohertz, then you can use these two values by default, like it was given in the data sheet as well as these are the design values for 15.1 kilo ohm and 1 nanofarad or 1000 picofarad for 110 kilohertz frequency. Okay, so the value that I was showing you here is not actually 100 kilohertz, it is 110 kilohertz. Actually it depends, like what happens is the graph is very small, so it is very difficult to fine tune or find a accurate value, so we have to always go ahead with some of the values that is given in the data sheet. Okay, now let's get into the design. So what we'll do is we'll have a detailed design description. So in that you can see, let's make it little bigger. Okay. Okay. So as you can see, we have UCC8C4x. Okay, so that is I will talk about UCC28C44. It is applicable for all other range of the devices in this series. So a series of control integrated circuit provides if the feature of necessary to implement AC/DC, DC/DC, fixed frequency control, current mode control schemes. Okay, so basically what are the things? It is going to give you an like all the features that is required for your AC/DC converter or DC/DC converter for fixed frequency control mode schemes. Okay, so there will be a fixed frequency of switching as well as current control modes with a minimum number of external components. You will be requiring very minimal number of external components. There you will not be like needing to have a very complex design, and as well as you don't need to have very high cost like inclusion into your design. You have protection circuit include under voltage lockout as well as current limiting both, so it won't fail in that case. Let's get into the block diagram of this particular device. So as you can see, we have VDD pin which is going to be have a supply VCC, okay, or whatever the thing. We have V reference pin that is coming from a reference voltage reference or something, or maybe kind of a regulator, okay, so which is going to give you 5 volt reference. All right. We have under voltage lockout facility here itself, so you have the reference and it will not allow this enable signal to work only before it reaches to a particular value. So that is the under voltage lockout protection that is inbuilt inside the IC. So this is a very good idea about the power supply schemes that is there, right? Coming back to the oscillator, so there are RT and CT pin which is going to set your oscillator frequency inside the system, and this oscillator frequency is going to switch on basically on the set frequency settings. Okay, you have the feedback pin which is going to go through an error amplifier with a 2.5 volt reference, you can see here very easily, and this output pin is getting regulated particularly like okay, this has been connected through V reference as a power supply, and this is going to set the reference voltage inside for this error amplifier, and this error amplifier is going to regulate the output voltage that is there. We have compensation pin also, so if you want to switch off this particular or shut down this particular PWM controller, you can force it to 0 duty cycle, or otherwise this compensation can be used to compensate this particular internal circuitry. We have current sense pin which is going to be used as a like a current setting or current sensing whatever the current is coming through the drain of the MOSFET. Okay, so this was all about this particular block diagram. Now coming back to the output side, so as you can see, output is being driven by a push-pull configuration MOSFET, you can see here, right? So this is driving in like totem pole conditions, totem pole formats. So this push-pull format is going to give you an output signal of around 200 milliamperes of current and the output voltage that will be going to drive the MOSFET. Okay, good. So let's get into the more features that is there. Okay, so if you see, we had like earlier UC2844, okay, and now we are going to have UCC28C44. So 28C44 is much more capable compared to UC2844. Okay, so if you see supply current at 50 kilohertz, which is way smaller than this earlier one, which is going to be just 2.3 milliamperes. We have a startup current just like 50 microampere compared to 1 milliamperes. Overcurrent protection propagation delay is just 50 nanosecond. Earlier it was 150 nanosecond with UC28C44 device, UC2844 device. Okay. If you see reference voltage accuracy, this has been reached to now plus minus 1%. Earlier it was plus minus 2%. We have error amplifier voltage reference accuracy plus minus 25 millivolt now. It was earlier plus minus 80 millivolt. So there are a lot of improvements that has been happened in UCC28C series. Okay. Coming back to the oscillator frequency, earlier it was up to 500 kilohertz, now it is 1 megahertz. Okay, and we have output rise and fall times 25 nanosecond. This was earlier 50 nanosecond. and the under voltage turn on accuracy is plus minus 1 volt, and here it was earlier 1.5 volt, and it has been now there in a VSSOP package and MSSOP package. Earlier it was SOIC package. Okay, so this was all about this. Now what are the things that we have to look into while designing this particular circuit? Just now I told you is basically we have to have my compensation circuit, then like a feedback circuit design, then current sense pin design, then we have RTCT pin design, and then ground and output. That's all we have to see, and we have to supply a voltage label, and my V reference is always there, which is going to be this is not 2.5 volt, this is 5 volt, I told you, right? So this is going to be 5 volt. So V reference is 5 volt plus minus 1%. Actually VFB was 2.5 volt. Okay. Good. So these are the 4-5 parameters that we have to see to design the complete circuit. So let's talk about that quickly. So what we can do is, very first thing, let us talk about under voltage lockout. Okay. So if you see under voltage lockout, what is happening is, for different devices, you can see 28C42. So 42 is going to have under voltage lockout on minimum 14.5 volt, and off time it will be 9 volt. So our aim is go ahead with 44. So 44 pin will be working, under voltage lockout on will be 14.5 volt and off will be 9 volt. Okay. So our aim is to use this particular device. If you want to lower the voltage of working, like a working voltage is lower, then you can go ahead with 45. Understood? Or even 43. But 43 will be working with 100% duty cycle, and these will be working with 50% duty cycle. So I prefer these devices with 50% duty cycle. Okay. Coming back to iSense pins. So you know already that iSense will be monitored as VCS by RCS. Okay. So let us say we want to design for 1 ampere. Okay. So 1 ampere, what will happen? 1 volt by 1 ohm. So RCS will be used as 1 ohm resistor. That's what you have to have. But I already told you the capacitor. This all depends on the capacity of the MOSFET that you are going to use, and based on that you will be setting. So whatever the current setting that you want to set, accordingly RCS will change. So what will be RCS value? RCS value will become VCS divided by iSense. So let us say my VCS is fixed to 1 volt always. So whatever the value, as iSense is increasing, my RCS will be decreasing, right? My RCS will be decreasing as my iSense will be increasing. So let us say for 2 ampere it will be half ohm, for 5 ampere it will be 0.2 ohm, so 0.2 ohm. So that will be my value of current sense resistor. Now this current sense resistor can be directly connected to the CS pin of the device. Otherwise what you can do is, you can have a RC filter. So this is my RC filter, which is going to be, let us say so this will be my RCSF and CCSF. So that will be, let us say 100 ohm and 0.1 microfarad is a general value that you can always use, and this is how you will be making it. Let's get into the oscillator frequency. So oscillator frequency, as I already told you, to connect that oscillator setting, what we have to do is, RRT we have to connect from RT pin to V reference, and one capacitor will be connected from RT pin to or CT pin to ground. So this is what this is how we are going to set my oscillator frequency. Okay, and the value of RT and CT we already calculated, that we can use, let us say 15.1 kilo ohm and 1000 picofarad or 1 nanofarad for those two values. Okay. Coming back to soft start timing. So let us say what happens is, sometimes we want to have a soft starting feature or something like that. Then in that case what we can do is, we can clamp this V reference diode with V reference pin with one diode. Okay, so this can be clamped together, and at the same time what we can do is, we can have a PNP MOSFET to drive this slowly. So this is how it can be called as a soft start feature. So if you want to have a soft start feature, what we can do, we can have one p-type MOSFET which will be helping the IC to start softly through the compensation pin, and feedback pin is already designed, so this is nothing to worry about. Right now we have to add only two components. One will be clamping diode to the V reference pin, and at the same time we will have to have PNP MOSFET. Okay, so you can use PNP MOSFET or even PNP PNP transistor or PNP channel MOSFET, both will be fine. Okay, so P channel MOSFET or PNP transistor will be used for this particular purpose of soft start. The only thing that we are remaining with is enable and disable feature of this particular IC. So as I already told you, the compensation pin can be used for enable disable feature. So what we can do, we can simply use one MOSFET to enable and disable through one microcontroller signal or something like that. So MCU signal high or low can make it disable or enable. So what happens is, whenever you make it high, so it will start working, and in that case it will get grounded and it will be disabled. Okay, and if you want to enable it, then what you have to do, you have to make it low. So once it goes low, then it will be enabled. Understood? So whenever you make it high, it will be disabled. Whenever you make it low, it means compensation is not connected now through the ground, and this is how it will get enabled. Okay, good. So this was all about this particular IC that we have talked about in the complete design and detail and everything. What we'll do is, we'll see one of the typical application that is given in the data sheet and how nicely they have made it. So as I have been already telling you, I am not going to explain these things. However, this is the AC input and all the safety features and circuitry. Then this is my bridge rectifier to rectify the output voltage. Okay, so this rectified output, okay, is going to go into the transformer. Okay, so this is my flyback transformer kind of thing, you can see. And we have other current, like other circuitry also, like RCD snubber and like auxiliary output, all these things are there. So we have here two outputs actually. You can see here one output is 12 volt, another one is 5 volt. So there are two, like this transformer is giving you two outputs right now, but both are flyback in flyback in nature or flyback mode. Our main purpose is to design this particular UCC circuit. Okay, so UCC3844 is being used for this particular application. And as you can see, this is my supply that is going to my VDD pin. Okay, so through this particular resistor and this diode and all those things are making sure that this VCC pin goes to here. Okay, and this will be around like 15 volt with one capacitor as well. Coming back to the other part, let us say output pin. So this output pin is going to drive the MOSFET, this particular Q1. So Q1 is being driven by this output MOSFET through this RD snubber circuit as well. Okay, so this RD snubber circuit is going to actually reduce the or help you to reduce the ringing or something like that at the gate of the MOSFET while starting of the switching. Okay, coming back to the this is simply ground pin. Now let's get into the current sense pin. So what is happening is, this is my drain, this is my source. So drain to source current is happening, and this is what is the RCS, like current sense resistor. So this current sense resistor is getting connected to my RC filter, which is, this is my resistor and capacitor, and then going to go to the CS pin. Hope you have a very clear idea about CS pin, how it is connected to the source resistor to the CS pin. Okay, now to set the output voltage setting properly, so what happens is, this output voltage like 12 volt and 5 volt has been used here, right? And this is the optocoupler that is going to be used to send the compensation signal towards the input side. Okay, so you can see here we have particular this particular pin which is going to come through this optocoupler IC2. So IC2 is here, and this is going to go into the compensation pin. At the same time, this feedback pin is utilizing this like emitter output of this this optocoupler. This is collector output, this is emitter output. This optocoupler FB pin is being used. Okay, so to set the FB pin, we have also utilized here voltage division of this resistor. So you can see here R52 and R53 and R54. So they are going to decide your feedback pin voltage, okay, feedback pin voltage level, and at the same time we have a reference IC, okay. So this is kind of like a sun type reference, or like a reference voltage, let us say TL431 you can utilize for this particular purpose. So TL431 is generally used for this particular reference voltage setting, and this output is going to get into the primary, or like towards the feedback side of this particular IC through optocoupler, okay. Coming back to the RT and CT pin, so as you can see we have V reference pin which is getting connected to my RRT resistor, and then CCT capacitor is getting grounded. So this is how it has been utilized, okay. One more thing what you could do is you can connect one capacitor to the reference pin which is connected here, that you can see. So this is what, so this was all about a complete design that we have seen each and every parameters, like how to power supply the VCC pin, how my output pin is driving the gate of the MOSFET through an RD snubber to reduce the ringing effect, okay. Then we have the grounding, then we have RT and CT pin to set the switching frequency or the oscillator switching frequency, okay. So RT CT pin we have done. We have current sensor resistor pin, so this CS pin is going to get connected to the current sensing pin, okay, current sensing of this particular resistor. We have feedback pin, so this feedback pin is getting utilized to regulate the output voltage to 12 volt and 5 volt, and at the same time compensation pin is used to compensate the IC control systems, okay. So this is how it can be used, and this is also a offline application which is with isolated version. So you can see we have utilized optocoupler to isolate the output and input side, okay. So this is what the complete design was. We have other designs as well, so if you wish to, you can have this particular design requirements table, and then like you can see we have design requirements as, let's say, 85 and 265 volt RMS. We have line frequency as 56 to 60 hertz. We have the output voltage requirement is 12 volt, okay. So you will use 12 volt IC. Then we have ripple requirement of 100 millivolt peak to peak. We have output current requirement of 4 amperes. The switching frequency requirement is 110 kilohertz, and efficiency is 85%. So if you any typical design that you want to do for your system, you try to fill this table for with your specification, and you can come up with a particular design that is there. So this particular design was there. You can have a look into the design data sheet itself, okay. So this design also is given in the data sheet, and this design can be always looked into. Just now I explained the way I explained you this particular design. Same way you can have a look into this design also. Anyway, what we have done is we will be giving you a particular design that is used in our devices in our next session, and that particular design will help you to understand what are the different parameters that has been used in a actual application that we have for our several consumer applications, as well as industrial applications. So alright guys, hope you have now a very good understanding about what is PWM controller and why it is preferred, because of its very easy design and low cost design, and at the same time you don't have a very complexity or very high complexity in design processes, okay. So if you do have any questions regarding your PWM designs or PWM controller selections, or what are the things that we should take care while selecting a PWM controller, please put down your questions in the comment box, or you leave out your feedbacks, or whatever the things that you want to have during the circuit design concepts, and we shall be giving you answers as soon as possible to our best. Thank you.